Yeah, thank you for the introduction. First and foremost, I would like to thank the organizers for giving me a chance to come here and present our results and for generous support. Today, indeed, I'm going to talk about how we can alter the structure of additional dichalcogenides using electron beam, and also about calculations related to electronic structure of dichalcogenides and some other systems. Jumping ahead of the story, I am a theorist, but I am working in collaboration with many experimentalists, specifically electron microscopists, and I shouldn't take any credits for the beautiful TEM images I'm going to show today. Prior to proceeding to the main body of my talk, I would like to acknowledge members of my group. Even though these two guys moved away from Helsinki, we keep on collaborating, and I would also like to thank many co-workers in Finland and worldwide, mostly experimentalists, and specifically Ute Kaiser and Simon Courage, her PhD student. Here they are during the research visit to Finnish National Park. And also another microscopist, Kazu Suinaga. He's also in Helsinki, but he's in the restaurant, very happy with the excellent Georgian wine here. Here's the outline of my presentation. I don't need any introduction what the dichalcogenides, so I'll move on to response of dichalcogenides to electron irradiation. Then a little bit about impurities in molybdenum disulphide, specifically about impurities which can be introduced during the growth stage, and also using post-growth methods, essentially using electron beam. Then about ultimate limit of impurities, basically mixed materials to random alloys, 2D alloys. And then a little bit about advanced calculations for electronic structure of molybdenum disulphide and heterostructures. And at the end, a little bit about 2D silica. It's not silicene, it's 2D silica, SiO2. Okay, so let's start with the response of traditional dichalcogenides to electron irradiation. Molybdenum disulphide and other inorganic 2D materials are routinely characterized using transmission electron microscopy. So electrons go through the sample and they may create defects. This example of the TEM image. This is another example. The image looks pretty good, but if especially microscopist trained eye may notice some features here and there. If you process the image, basically filter out the noise, we'll see that the sample is actually not that perfect as it may have looked. There are quite a few vacancy type defects. So one of the questions is, where do defects we see come from? Are these irradiation-induced defects, or are these intrinsic defects in the sample? Okay, to answer this question, we understand how defects in TEM are produced. And like in this slide is a crash course about damage in transmission electron microscope. The first source of defects is ballistic knock-on damage. Basically, electron hits the atom and assigns some basically transfers kinetic energy to the recoil atom. In graphene, it may be something like that. Electron beam is coming from below, and then when the element is displaced, and in this case, we see formation of vacancy and a atom pair, just an illustration of what happens in materials under radiation. This mechanism works in any material. Then we have ionization and electric excitations. This mechanism is mostly relevant to semiconductors and insulators. Essentially, electron knocks out secondary electrons, so material may get positively charged. We may have Coulombic explosion, and if we excite electrons to antibonding states, then if residential time is long enough, we may have defects created in the material. Finally, we may have beam-induced chemical etching. Vacuum is never perfect. We break up molecules, energetic electrons break up molecules. Then we have chemical reaction, and eventually we may have some sort of etching. For example, CO2 evolution from graphene. In fact, all these mechanisms work depending on the specific system and electron beam energy. For example, in graphene, you can separate ballistic collisions, ballistic damage or knock-on damage, and actually chemical etching. If you grow up graphene from carbon isotope from carbon-13, because chemistry is exactly the same, but mass is different. I don't want to go into details. I just illustration that you can differentiate these effects. Okay, so it's moly disulphide sample with some defects, which are clearly seen here, vacancies. And we try to understand from the pointer theory at what voltages defects appear in molybdenum disulphide. So to do this, we carried out DFT calculations. So essentially, we assigned kinetic energy to the recoil atom, mimicking impact of energetic electron, and calculate the displacement threshold. And then, if we know displacement threshold, that means the minimum kinetic energy you should assign to the atom, so it leaves its position without immediate recombination. Then we can calculate back the electron kinetic energy or correspondingly the voltage. Basically, we can displace only sulfur. Selenium and tellurium are way too heavy, but the same works for, the same is true for metal atoms. With standard TM, I mean with 80 or 60 kilovolts, that's the standard voltage at which microscopes operate now. But I stress that the molybdenum disulphide, it's not the only mechanism, because if you look at the experimental point here, blue point, and blue curve is theoretical data, the displacement rate is much, in the experimental value, is much higher than the theoretical one. So this means that ionization and excitation should also be important, or possibly chemical etching, because defects also impair molybdenum selenide under radiation. Okay, so these are examples of various defects which appear on the electron beam, and pretty much, well, sorry, I was too quick. Different single die vacancies in like on top of each other or in different places in molybdenum disulphide. Pretty similar results were obtained recently by another group. Here examples of the same defects from their paper. Now let's put sample into TM and keep it under the beam for some time. This is the movie, and you may see that some linear structures appear, like this, or like that, like this here, again, another one here, and will appear also there. I hope you can see them. These are, in fact, vacancy lines. Vacancies tend to agglomerate and form lines. Vacancies can agglomerate in different configurations. For example, this is a single vacancy line, di-vacancy line with vacancies in different layers, I mean sulfur layers, or like staggered configuration here. Based on our calculations, it appears that only some configurations are energetically favorable with respect to isolated vacancies. And exactly these same configurations our coworkers see in experimental TEM images. So they are configurations for which the energy goes down. So this means that vacancy type defects tend to agglomerate in molybdenum disulphide. Now the question is, what's the mechanism of this line formation? So let's take basically a blow up of one of the slides, and this is the slide from the movie after 1 second. We clearly see that in the upper part of the image, the vacancies collapsed into line defects, while in the lower part of the image, here vacancy is the same as this and that configuration. How this happens? So Of course, migration can be responsible for this, and we indeed see that, for example, vacancy, which was over there, migrated to a new position. Okay, now it's here. But from the point of calculations, the barrier is pretty high. It's about 2 eV, so no way for efficient migration of vacancies at room temperature. And beam heating effect should be negligible in this case. Even if we assume that electron beam induced diffusion is active, still this cannot explain the observation. But if we calculate formation energy, if we calculate migration barrier for vacancy when another vacancy is nearby, the barrier drops quite a lot to like 0.7 eV. And this may explain the sudden collapse of the atomic lattice. Basically, when concentration of vacancies increases, at some point lattice becomes unstable and line defects are formed. Now a bit about impurities. Let's start with impurities which can be introduced after the synthesis in TEM chamber. Again, I would like to remind you of all the junk which we have in the TEM chamber, or in principle, we can deliberately put some molecules into the TEM chamber, especially in environmental transmission electron microscopes. So when you break the molecules, and if you have vacancies, the atoms will stick to dangling bonds, which are highly reactive. So depending on what we put, we can get P-type or N-type doping using this post-synthesis method. These are band structure calculations for different impurities in molybdenum disulphide. And of course, all of them, all the configurations are energetically favorable because dangling bonds are chemically very reactive. So it's unfavorable to have dangling bonds, or basically vacancies in molybdenum disulphide. Okay, and this is piece of evidence from the experiment that some sort of in situ annealing of defects, basically passivation of dangling bonds happens. So here we have vacancy production, and at the same time, in this particular place, some atom heals the vacancy, but we do not know if it's sulfur atom or something else. It's quite difficult to differentiate from the experimental TEM images. Now about intrinsic doping. So here we have examples of rhenium-doped molybdenum disulphide. And these bright spots are rhenium atoms. Actually, this project was carried out in collaboration with Kazu Suinaga, who did microscopy, and also this Huang from Taiwan, and Dmitry Dumchenko, who is now working for András. Okay, so basically, these are examples of rhenium doping, and the rhenium atoms are in substitutional position instead of molybdenum. And this is gold, but gold atoms prefer to be on top of molybdenum of the sample. They are more mobile, and they tend to agglomerate. As for electronic structure, rhenium clearly gives rise to N-type doping. You see this stays over there. This gold situation is more complicated because like isolated atoms, or to be precise, atoms, they give rise to states in the middle of the gap. But when gold atoms agglomerate and form clusters, then you may get P-type doping, or then gold atoms are attached to the edges of flakes. Then you can also get P-type doping. And the dopant atoms will locally increase reactivity. You, for example, in this case, you see agglomeration of carbon near the impurity atoms. So they may enhance catalytic properties of molybdenum disulphide, and some configurations are magnetic. In principle, this could be a way to introduce new functionalities to molybdenum disulphide. Now, about mixing atoms in transition metal dichalcogenides. Let's start with graphene and boron nitride. We know that graphene has no gap, boron nitride a wide gap. And a dream material could be, you pick up a boron, nitrogen, carbon atoms, you mix them together, and depending on the concentration, you can get any value of the gap from 0 to 6 eV or something like that. Unfortunately, in practice, this doesn't work, or to be precise, doesn't work well. There is some progress in this area. Graphene and boron nitride, they tend to segregate. At the same time, we know that bulk ternary compounds, semiconductors, they do exist, and the band can be tuned continuously. So the question is, if we take 2D materials and mix up atoms, for example, we can mix atoms in the chalcogen sublattice, sulfur and selenium, or mix up atoms in the metal sublattice, for example, tungsten and molybdenum. Will these compounds be stable? And the second question, what the electronic structure would be in this case? So I'm a theorist, so we can take atoms and mix them in the computer and then calculate total energy and free energy with a count for entropy of mixing. And actually we see from this plot that at room temperature, these compounds must be stable. And actually this, especially for sulfur selenide mixture, it really system wants to be in the mixed configuration. So from this kind of calculations, it looks like that this compound should be stable at room temperature, and mixing would be possible. Should be possible. So what are electronic properties? I don't have to repeat that once more, that single layer molybdenum disulphide is direct gap semiconductor, contrary to bulk materials. But now let's calculate the band gap for these random alloys. It's not a trivial thing, because we know that the band structure works in principle for periodic systems, and here we have no periodicity. But recently, Alex Zunger developed a very nice concept of effective band structure. The main idea is that you take a big supercell with random distribution of impurities, or basically your components, and then you calculate the band structure for the supercell, and then you project it back to the unit, to the band structure of the unit cell. Again, recall that the atomic structures for the alloys are pretty much the same. More or less the same unit cell size. And this works very nicely, and all the materials seem to be direct gap semiconductors. To some extent, it's easy to understand why, because we know that the valence band maximum and conduction band minimum, they are localized on metal atoms, on molybdenum in this case, and basically d orbitals here. Okay, so essentially, this is our predictions for band gap. It should depend continuously on the concentration. So once more, this is the plot. And recently, I became aware about two papers which are under review now. One coming from Ajayan's group, and this one from University of California, Riverside. They essentially confirmed what we predicted. So these 2D compounds, mixed compounds, are stable, and the gap can continuously be tuned. In this case, you mix up chalcogen atoms. We also predicted that this trick should work for metal sublattice, tungsten and molybdenum, for example. And actually, recently, two papers were published where exactly the same, again, was reported, experimental papers. So I was quite pleased as a theorist to see that sometimes our predictions come true, and moreover, we somehow managed to stimulate research in this area. Okay, so about electronic and optical properties of molybdenum disulphide and heterostructures. Well, these actually issues have been touched upon several times during this workshop, so I can basically do not need to repeat about excitons in molybdenum disulphide. But assume we know nothing, and we honestly run DFT calculations to see if simple vanilla DFT calculations can reproduce this transition from indirect to direct gap. Yes, we take two sheets and then decrease the spacing between the two sheets, and we see a nice transition from direct to indirect gap at some point, which corresponds to roughly the bilayer. And Everything is fine, but the value of the gap is smaller than it should be. But again, this is expected, so we can carry out more sophisticated GW calculations. Indeed, the gap increases, but if we plot the band gap, the fundamental band gap, I stress, as a function of separation between the layers, or inverse, we see very actually strange result. We see that the gap scales as 1 over d, the fundamental gap. And we arrive, if we look at the direct gap, something like 3 EV, which is clearly much more than experiments give. We were not the first who got this somewhat puzzling result. For example, this paper coming from Kirach's group, they also found this result quite paradoxical. Actually, we know the answer now, and there's nothing paradoxical here. If we calculate the excitonic binding energy, in this case, we just solved numerically the Bethe-Salpeter equation. The excitonic binding energy also scales as 1 over d. So if you subtract excitonic binding energy from the fundamental gap, you get these blue dots, which are very close to the experimental value. But to some extent, two effects counterbalance each other. We were really quite excited when we got this result, but then actually we learned there is nothing new in the world, in the universe. Already Ludger Wirtz and Angel Rubio, we received pretty much the same result for boron nitride sheets. We also calculated, by the way, the gap in BN using sophisticated techniques, even fully self-consistent GW, and the gap value is much larger than the experiments. So basically, so I would strongly encourage experimentalists, or at least think about the direction of if it's possible to measure the value, to determine the value of the fundamental gap in freestanding molybdenum sulfide or boron nitride or any other system, to really understand if this effect, which actually comes not only from our calculations, but calculations of other groups, in particular, well, I'll come back later on to a recent Stephen Lewis paper, who basically sees the same effect. Very interesting to understand if indeed the fundamental gap is so large as DFT calculations predict. Okay, so now if we look at how the gap depends on the environment, or the number of layers, with account for excitonic effects, excitonic binding energy increases from 0.1 to about 1 EV. We have very nice agreement between experiment, these yellow points, and calculated dots. So again, here looks like excitonic effects are quite important, as we know, and increase in the value of the fundamental gap, excitonic binding energy, they perfectly compensate each other. And this is a recent Stephen Lewis paper. They reported pretty much the same values. Once more, fundamental gap is considerably larger than the optical gap. Excitonic binding energy also grows up from 0.1 EV in bulk molybdenum disulphide to nearly 1 EV. Okay, so a little bit about staking. I essentially included these slides after these morning presentations. We also looked at staking of molybdenum disulphide with other materials, but contrary to many other groups, we decided to make up the supercell properly, in the sense that we'll try to minimize the strain, because we know that even like a couple of % of strain may induce spurious effects basically the strain may affect the band structure and give rise to spurious effects. Because normally you have materials have different unit cell sizes, and in the within the supercell approximation, you should find construct a supercell basically by rotating one of the systems in such a way that you get the same supercell size for each of the sublayers, and then you can construct a periodic system from this. Well, making the long story short, we calculated band structures, but before I move on to the band structures, I would like to emphasize that van der Waals interaction is important. And as I mentioned this morning, the value of van der Waals interaction depends on the model you use. The most accurate way to calculate van der Waals interaction now is a so-called random phase approximation. Basically, it's some sort of perturbation theory on top of standard the DFT calculation. I don't want to go into details. So assume that 0 is the exact value. PBED is Grimmie correction, these purple points. As we can see, for example, for molybdenum disulphide, where is it? Here. The agreement may be not that bad. But for some other materials, we have a really big, about 60% difference with regard to RPA value. So once more, we should be careful when we use a Grimmie correction approach to calculate van der Waals interaction here. And as for van der Waals interaction, it seems to be some sort of universal quantity, which only weakly depends on the compounds. It really doesn't matter if a system is metal or semiconductor. The values are in pretty narrow range. And exceptions are normally the materials where you have weak covalent interaction. If you switch off van der Waals, you may still have weak bonding coming from essentially overlap of the orbitals, weak covalent interaction. Well, if we know binding energy, we can calculate exfoliation energies and all other quantities. And here I would like to stress that we have very good agreement for graphite. But as for dichalcogenides, we have disagreement by a factor of 2 experiments coming from actually liquid, solvent exfoliation of the materials from Janis Coleman. And other groups reproduced our results, so to this end, it's not, we are sure that we didn't make a stupid mistake. So this means that either we have a fundamental problem with DFT, which I doubt, or something in experiments, very tricky experiments on solid exfoliation, the binding energy is determined. So once more, appeal to experimentalists, maybe, or a suggestion, if you could have a look at this issue, this would be really interesting from the point of fundamental physics. Okay, so in this, how band structure of the material changes when you stack molybdenum disulfide with tungsten disulfide or some other materials. Basically, as already several speakers mentioned today, when you stack 2 materials, mostly the states near the gamma point, they change a lot, and at the Dirac point, the changes are much smaller. But what's important, we did optical absorption calculation for molybdenum disulfide, tungsten disulfide system. And the thing is that even though the band structure changes, the absorption spectra are pretty much the same. So this means that mixing of optical transition is quite small. The layer transitions are negligibly small. So this means that if you change the electronic structure, this doesn't mean that you also change optical properties. At least you should be careful when you predict that. Unfortunately, we couldn't do calculations for other materials due to computational limitations here. Okay, now I'll move on to the last topic of my talk about bilayer silica, its structure, and defects. So this is an old cartoon by Zachariasen, published in 1932. This silicon structure, 2D structure. And recently, my co-workers, when growing graphene on copper, in TM images found quite peculiar structures which looked either like periodic or were random. This is more or less. And we actually, from EELS, we realized that oxygen and silicon is involved, which actually accidentally came from quartz tube used in the apparatus for growing up graphene on copper. And basically, we theorists, we worked out the atomic structure, which should be something like that for the periodic system. Later on, actually, we found that this structure had been synthesized already on several metals by Berlin group, and silica can be exist as a monolayer or bilayer, which is only weakly bonded to the metal surface by van der Waals interaction. And recently, together with another group, Florian Banhart, actually we looked at the silica structure on ruthenium and some on iron and some other metals. So why silica, bilayer silica is interesting? Well, it's thinnest gate dielectric oxide layer and can be used for catalysis. And recently, Silvano Lizit published a very nice paper where he intercalated very thin silica layer between graphene and metal. But to this end, using this trick, you maybe will not need to dissolve metal and transfer products. Isolation of graphene from metal may be somewhat easier. But anyway, silica by itself is quite interesting. So this example, basically, this are structures. It's single layer, which is covalently bonded to metal, but with and without metal. It's to some extent it's similar to silicene. It's a epitaxial structure, but silica bilayer, it's only weakly bonded to the metal, and it can exist on graphene and possibly maybe even freestanding structure. This is the atomic structure of silica bilayer. Now let's look at defects in silica bilayer and graphene. We just published a paper on that, and jumping ahead of the story, defects in graphene and silica bilayer, they follow, in two systems with completely different properties, but the same symmetry. Defects follow the same pattern. Okay, I would like to remind you that in graphene, when you take out a carbon atom, it's energetically quite expensive, but under radiation, under beam radiation, it can happen. You have a Jan-Teller reconstruction of single vacancy, formation of the pentagon here, and the same works for for die vacancy. So you have a formation of new bonds here, and this is not the end of the story. In fact, in graphene. Actually, if you take this bond, rotate it like that, you end up at the constellation of non-hexagonal rings 55777 defect, which actually has lower energy than original non-reconstructed die vacancy. And all these defects we have seen in, or to be precise, my co-workers have seen in experimental TM images of graphene. Moreover, in graphene, electron beam can induce stone-Wales transformation. This movie shows how the bond is rotated. And our simulations indicate that probably when electron hits from below, atom is almost sputtered away, but it's still attracted back. And you get a stone-Wales defect this way. Now, let's look at SiO2 bilayer. We also have a stone-Wales defect in SiO2 as in graphene, and actually we can see in the real time this formation of stone-Wales defect. But in SiO2, the process is much more complicated. It involves knocking out oxygen atoms and then probably restoration of the bonds from oxygen coming from some other areas. So it's much more complicated than in graphene. This flower defect is really a beautiful structure. You do 6 stone-Wales rotations in graphene, or correspondingly, this is graphene, so you can do it like start from pristine graphene and do the 6 rotations and end up with flower defect, or the other way around. This is flower defect which disappears. Now it's gone. you basically goes the opposite direction. So you end up with pristine graphene, all the atoms are there. So, example of flower defect in graphene and in SiO2. Exactly the same structure, scale is different, and structural unit in graphene is just a CC bond. In SiO2, it's silicon-oxygen-silicon bond. And formation energy of this flower defect in SiO2 is much smaller than in graphene. So we have here dye vacancies and reconstructed dye vacancies called butterfly defect. It just rotated, examples in graphene and in SiO2. And there is also similarity in the energetics of grain boundaries in graphene and bilayer silica. Finally, I would like to note that SiO2 exists as crystalline and amorphous material to the amorphous material. And you can also make amorphous graphene by treating it under very special conditions. You first create some defects, and then you irradiate with electron energies below the displacement threshold. So you have lots of bond rotations. So the system remains more or less coherent in the sense that it does not create holes, but it's heavily randomized. So there is also this similarity, and finally, in principle, we can envisage existence of Haeckelite structures both in SiO2 and in graphene, but actually in carbon systems, sp2 hybridized carbon system, it costs much more energy than in silica. So this is a new member of 2D material family, which may be useful for isolating one material from the other. And contrary to boron nitride, well, boron nitride can also be grown on top of graphene. It may be intercalated between several layers, so maybe again new way for engineering vertical heterostructures. So basically, this is all what I wanted to tell you today, and thank you for your attention.